on this computer. There we go. Okay. All right. So you're all very welcome. Oh, just one sec. I'll close the door. I probably should have done this. You're all very welcome to the Dublin Data Science Workshop for August on this fine August evening in Dublin. Apparently we're going to have a good week of weather. I know there's a couple of people have connected in from overseas. If anyone isn't in Ireland, would you just mind putting into the chat where you're connecting in from, just so I have a sense of the geographical spread, if you wouldn't mind. Obviously, if you've got privacy issues, that's fine too, but just to get some ideas, there are people here who aren't from Ireland. That would be good to know. I know we have at least one, but sometimes we have kind of a couple more. So it's just purely from my own kind of curiosity and all that. Okay, so what I'm going to do today is we are doing this data science soup to nuts workshop. The idea was we kind of got a bunch of questions as part of our Dublin Data Science meetup. We kind of got a lot of questions about people either starting out or in the middle of a project, or how to go about things, and just all sorts of kind of ins and outs. And it occurred to me that while, you know, there's loads of really, really good stuff out on YouTube, and please correct me if I'm wrong about this, I haven't found anyone actually kind of going through either a project. Now, it's possible it was done and just all you can see online are the slides, but there's certainly no one anywhere doing a project from start to finish. And that's kind of what the whole soup to nuts expression means. Initially it was like when you were eating fancy in, you know, the 18th century or something, you started with the soup and you finished with the nuts. So it kind of means from start to finish, and it's just a fancier way of saying that. And I thought, you know, let's try and be a little bit novel here and call it something different. And you'll excuse me, I will be drinking tea while I do this to keep my throat lubricated. So the whole idea is we take a data set from the very start. We talk through the various issues of how the project is done, the various compromises that are required. You know, how do we think about what's good and what's bad? How do we figure out what to do and what not to do? How do we, you know, how do we think about what makes for a good model and what makes for, you know, a not so good model? Hi, Daniel, would you mind? You've just unmuted yourself. Would you mind just
sorry with that? Yeah,
not at all, not a problem at all. Yeah, I'm not, just because I know sometimes there's background noise and stuff from various individuals. By all means, by the way, if you have a question at any point for any of the rubbish that I'm talking, by all means, you know, pop a question into the chat or just unmute yourself and ask. Like, there's not too many on this. We've got what, like 16, and that's 2 of them are me. So we've only got 14 people. I'm more than happy to kind of, if people are happy to you know, ask a question in person, by all means unmute. But if you'd prefer to put it into the chat, like I said, I am kind of monitoring the chat. So if there's something I'm not explaining particularly well, or you want me to go over, or there's anything you need me to kind of discuss or whatever, please by all means. Oh, Malcolm, do you mind putting yourself on mute? I will mute you. There we go. By all means, just kind of, you know, interrupt me, ask away. This is probably going to be the most, how would I phrase it, statistically advanced of all the workshops we're going to do. And as a spoiler alert, we're going to talk about buy till you die models, which are very common in retail, which is kind of how I you know, and that was kind of one of the reasons for actually doing this workshop, was kind of to keep me interested. I wanted to work on a data set that I'd never really worked on before, like that type. And I'd done some very simple stuff, but I've never really worked on like a purely transactional data set before. And I thought that would be kind of an interesting thing to do. So I've been kind of, that was kind of the interest for me. And I knew about buy till you die models from various individuals, and, you know, through the Dublin Data Science, and it always struck me as an interesting kind of model and approach. So yeah, that's kind of what we're going to cover tonight. But despite all that, we're not going to include it in like the final project, like in terms of what we would in our kind of virtual world hand over to the stakeholder or the ultimate client, or whatever way you want to do it, your boss, however you want to think about that. And there's a couple of reasons for that. But the main one is that these are relatively sophisticated statistical models. And from a communication and like modeling perspective, I actually don't think you need to go this sophisticated. So while I'm covering them for the purposes of tonight, I actually thought about not doing this workshop at all in terms of like skipping this topic completely. But again, the idea was to kind of show the whole process from start to finish. And one of the key things that never really gets talked about is the dead ends you go down. And this is a pretty big one, because most of the other things that we've talked about so far in this project, and all of these are available on YouTube, and all the code for this is online. I will actually, at the break, I will post the GitHub repo that this is all in. Most of the stuff we've done so far will, if not directly, kind of be in the final thing that the final modeling workshop or whatever, the final piece of work. This one probably won't be. In fact, when I say probably, I mean definitely won't be, because it's my call. And the reason for that is, while the concept of this is very interesting, and I think it's a really powerful model, first of all, the scope of it is it's kind of beyond the scope of this project. This project isn't about doing, buy till you die models. The whole point of this series of workshops is to kind of explain the process as at least I understand it, and kind of some of my peers, and kind of just from discussions, we've kind of evolved a way of working. Now, which is not to say that we would all approach this similarly. I can imagine most of the kind of the main people that attend, Dublin data science workshops would approach this in a very different way. But, with the overall kind of general ideas be the same, even though it would probably look very different. But I kind of, because of that, because what we're just trying to do is just get something modeling and show the entire process, this I just think is just a step too far. It's more complicated than what is necessary to complete the project. So as much as I love this modeling, and I think it's really useful, I'm going to talk about that today, and I can actually see a whole bunch of applications for this kind of general approach in other areas. This stuff is not going to be in like the final thing that we present to the client, for want of a better term, because I think it's too complicated. I think we can do simpler things with our RFM models, like we discussed in the last workshop. I think that actually does the job. I think that will do more than enough for the purposes of conveying something useful. We can do a few other interesting things that we'll probably talk about in the next workshop. But what I'm doing this week isn't necessary. However, I think it's useful to cover it for a couple of reasons. One, I think it's just a useful technique to learn. And this is the kinds of things that you shouldn't be afraid to do. Like, all this work is research in general. I mean, the kinds of things we tend to do when I think of data science, I don't think of, it's not an engineering project. So you don't have predefined goals beyond, like, certainly nothing concrete. Things tend to be very woolly and a bit, ill-defined. So you might have some very random targets that you want to go, we want to get a sense of which of our most valuable customers, let's say. Well, what exactly does that mean? And then you go down that particular rabbit hole. But what I do want to focus on is give the basic ideas of the model, and then kind of justify why we're not including it, if that makes sense. Because in my experience, this is almost certainly going to happen to you in your project. So there are things you're going to do that either you hit some landmines, which some of those landmines we're going to go over today, or you kind of intuitively understand it, but explaining it is going to be complicated. And if that is the case, that's not something you should be doing at the start of a project, unless you have a lot of buy-in and the easy work has been done before. So like, if all this work has been done before and you're coming in to kind of to do this, to take the basic work and then build upon it, that's absolutely fine. But in most cases, that's not what's happened. In most cases, you're either starting from scratch, or you're taking a new way of looking at a data set, or you've got you don't have particularly clearly defined objectives. And in that case, and it's a tool, it's a a sermon I've always preached for a long time, is that, it's the old Einstein maxim of as simple as possible, but no simpler. And I think from that point of view, these models just are just not simple enough. They're, you end up explaining a lot of things. In some cases, they're kind of tricky to fit, which also, is a bigger thing. But it is a very useful, it's also useful to have at least looked at it and spend that, unless you're under severe time pressure, it's good to know. You're better rather than not looking at it at all, because it's such an obvious thing to look at, because it's a very standard approach now, at least from what I can tell. That's why we're going to kind of look at it but not do it. So I know this is a bit of a weird one, because I don't know what workshop this is. It's probably 5 or 6. I'm sure somebody out there know. All the rest of it has been, very end oriented, and we've been very focused on doing something, getting to the end client, getting, to the end goal, and figuring out what to do. This one is a little bit of a diversion, but I'm going to capture again, kind of like the example of the negative results that no one ever talks about, that are incredibly important to the process, which no one ever talks about, because from a scientific point of view, it's not publishable, which I think is often a shame. But because sometimes you learn an awful lot more from the negative results than you do from the positive results. Not that these don't fit at all. It's just that, there's a few things going on. So so we're going to cover all of that. Before I begin, I'm very conscious we have new people here. So I just want to do a very, very quick summary of, the previous 5 or 6 workshops, all of which are up on YouTube, by the way. I should mention this, and I will provide a link to it, or I think there has been links. There's links in a whole load of these workshops from where you can find them. I think the channel is Dublin Data Science on YouTube, and there's a Data Science Soup to Nuts workshop. At the break, I will probably do a screen share on it and share it up. So the format for today is we're going to go until it's a 2-hour workshop, which is generally what we do. For those of you who are new to this, generally we take a break around 8 o'clock, plus or minus 15 minutes. We take a break for about 10 minutes, depending on where we are in terms of, I try to come to a very natural break point. So I don't make it very strict to a time. It'll sometime between, say, 7:45 and 5 or 10 past 8. We'll take a reasonably fast break of 5 or 10 minutes. If anyone has any questions, or there's any kind of weird tangents that people have asked me about that don't quite fit into what I'm trying to discuss here, we can kind of talk about them there, or at the end, bathroom break, whatever. Just take a quick break, and then we'll get back onto it. And then I generally try to finish up sometime around 8:45, 10 to 9. But if people need me to go on, or questions or whatever, I'll try and finish the main content around 8:45. And then if there's any questions or anything going on, or you need me to go over anything, it gives us a bit of a time at the end. So that's kind of roughly how we're going to do it. So because we have some brand new people, let me just very quickly go through what we're doing. So like I said, the whole point of this series of workshops is to show a data science project from the start to the finish. Purely for me, I thought this would be interesting. I wanted to take a data set that was online. I got the online retail data set, Online Retail 2, which is available in the UCI machine learning repository. For those of you who aren't familiar with it, I'll show that at the break. It's basically a set of transactions for some kind of hybrid online, offline store, doing kind of like an Etsy or something. It sells like pillowcases and pillows and deck chairs and kind of random kind of houseware stuff. I'm not exactly sure. Unfortunately, the data itself doesn't come with a huge amount of descriptions to it. So we lack a certain amount of domain knowledge for this data set. That has led to quite a few questions, and there is a lot of kind of weird stuff in the data set. So the first 2 or 3 workshops were actually spent largely cleaning the data, a process which has been ongoing. There's a couple of things I've had to clean up even in this workshop that that kind of, you don't really become familiar with until you start seeing weird results as a result of the data. So it's a very kind of iterative process. We then kind of moved on to actually modeling the data itself, and we did a bunch of different things. We looked at some graph analysis based on, transactions, and so you've got products and transactions. So I created a graph where you have a transaction ID that contains a bunch of products in them. So those, the nodes are your product ID, and then your transaction IDs, and there's an edge between them if the product is in the transaction. We also looked at association rules, which models basically how the likelihood of one item or bunch of items being in the basket affects the likelihood of seeing another item. So we have those association rules. We looked at that. We looked very briefly at time series analysis and a couple of other graph models. We looked at something else. Let me just check the workshop in here. You can see there's a whole bunch of stuff in here. We did some graph data. We did a whole load of exploring the data and plotting it. The Data Explorer there is a package in R that I wrote my own worksheet in R Markdown that kind of does all my data exploration for me. And I found out Data Explorer about 2 years later, when I already kind of had it up and running. What I'm kind of slowly in the process of doing is incorporating their far superior stuff into some of the things I want to do. Looked at some time series, and then kind of the last thing we did was in the last step in the last workshop was looking at these RFM models, which is recency frequency monetary modeling, which is kind of related to the modeling we're looking at today, which is buy till you die. But the idea is kind of similar. You look at customers who have transacted most recently on your system, then you look at the customers who have transacted the most often in terms of counts, and then also in terms of how much they've spent. And you split them up into buckets and you kind of map them that way. And you come up with a very kind of simplistic segmenting system just based on quantiles of those parameters, and you partition your customer base into different buckets. And that kind of does the job. And that seemed to work quite well. And that's something we're kind of going to look at a little bit more in the next workshop. But to take the kind of that idea a little bit more with slightly more kind of statistical, using statistical modeling, we have what are called buy till you die models. And that, again, it's all part of this whole customer lifetime value thing. Interestingly enough, BTYD, they're being popularized by a guy called Peter Fader, who is out of the Wharton School of Business, I think. Although it was originally created in the early 80s. The first one was this Pareto Negative-Binomial Distribution model, the PNBD, which was originally used for brokerage clients. I believe Morgan Stanley, but don't quote me on that, but it was one of the kind of retail brokers, and they were just trying to get a sense of counting your customers, like what customers do we have, how often have they traded, what do they do, all that kind of stuff. So I know that might be of interest to some of the people here looking at the presences in the chat. So it could be quite interesting, like how exactly it's mainly used in a non-contractual setting. Where
all right, yeah.
Sorry, Kieran, do you mind putting yourself on mute? You accidentally unmuted yourself there, I think.
Right.
No, you're right. So yeah, so in a non-contractual setting, it's harder to tell whether you have a customer or not, whether they have churned or lapsed or whatever you want to call it, because you don't have those regular checkpoints of, like, if you're a phone company, you have these monthly payments. If you're on a utility bill, you have these monthly payments. If it's like anything like that, or even like life insurance, which is how I first started working on churn modeling, you're paying monthly premium or annual premium. It's a different model where you kind of know whether or not your customer is churned because they've stopped paying in these regular places. Whereas in a non-contractual setting, it's much harder to tell, because how do you know if a customer is no longer a customer, or have they just stopped transacting with you, or are they just kind of very infrequent? Like, so I might go maybe a couple of years without buying something, but it doesn't mean I'm no longer a customer of whatever web or whatever store. So when you've got that kind of essentially discretionary customers where they can come at will, it's a trickier prospect to say, well, do we think this customer has churned, or is the customer just no longer taking part? And, you know, at a higher level, you can actually start thinking, you know, a bit more, again, take it a step up and start to think, well, maybe this is the kind of customer that I don't hear from at all, apart from at Christmas time. And then there's a flurry of activity in October, November, and then I don't hear from them again until the following October, November. And that's a very different type of customer to a customer, say, who, you know, doesn't transact at all, but then will make a couple of transactions and then goes away for a couple of months and then makes another few transactions and then goes away for a couple of months and so on. So that, you know, you get all these kind of different types of behavior that that may or may not, you know, indicate that the customer has churned. So how do we get a sense for that, and how do we kind of start to model that and do something useful with it, and not just do it from the point of view of, you know, descriptive? Can we get some kind of quantitative measure of that type of thing? Okay, and that's basically what BTYD does. And I think it's very interesting. It's a particularly interesting model, which is why I kind of wanted to include it today, because I think there's a lot of uses for it, even outside of the you know, the online retail. Now, one of the interesting things I have noticed is, you know, now that I'm aware of the models, I started looking at them basically when I started doing this workshop. And it was, the initial idea for the workshop was that the main modeling I would do would be BTYD. But then I came across that RFM package and those simpler ones. And then once I kind of discovered that, I went, no, let's just do this simpler thing. Let's not bother with these fancier models. However, I do like these models so much, even though obviously I'm not really going to talk about them after this workshop. I am going to do a Bayesian workshop next year, which will focus entirely on these models and building them up on a statistical point of view. So it'll be, you know, it'll be shorter. It won't last, you know, however many. It'll probably be more like maybe 2 or 3, possibly 4, depending on how things go. But that's going to be exclusively kind of taking the Bayesian approach. And I'll talk about why I'm doing that today, even though I do tend to use Bayesian modeling in general. But there are some issues with fitting these models, which I've alluded to a couple of times now, that I think a Bayesian approach makes things more amenable to trying to kind of diagnosing those fitting issues and trying to get a sense of what's going on and where and why. And also it allows you to extend it much more easily into building in hierarchical models where, you know, you can have different kind of hierarchies of customers that might behave differently, all that kind of thing. Okay, so that's kind of where we are. I'm conscious we've kind of used up a bunch of time, but believe it or not, that's a lot less time than I usually spend doing the recap. Does anyone have any questions in the chat, or you know, anything that they would like me to? Did I mention something randomly and kind of scoop over it? Or, you know, if you have any questions, please put them into the chat, or feel free to just unmute and ask the question. In the meantime, let me just take a slug of tea and then we'll get started on BTYD. Okay. All right. So we have, oh, I'm sorry, you know, we have a whole load of plots of various visualizations and looking at some interesting patterns. It's amazing what you can find from just plotting the data. Like, for example, we don't think this is a fully online store because the shop seems to close down around Christmas for about 10 days. And that's because the data goes from, I think it's December 2009 to about the same time, 2011. So it covers about 2 years. And there are 2 periods of time over both Christmas periods where it flatlines. There's literally no transactions whatsoever for about 10 or 11 days. And if you notice it, it goes kind of Friday to the Monday, and they don't transact much at the weekend either, although I think they started towards the end of the data set. So you kind of have this, even though it seems to be an online website, they seem to observe kind of normal retail hours as opposed to buy whenever you want on the website kind of thing. So now that could be because of the time it was 09 and 11, and maybe just the regular having everything online all the time was just kind of more complicated in terms of how they process the transactions or something like that. I'm not entirely sure. All right, so one thing I will quickly do before we start is just talk a bit about what the data looks like. So this is, oh, let me zoom in a bit more on that, because I'm conscious that can't be seen. is 160 is probably. Is that large? Can you just let me know in the chat? Is that large enough for everyone to read on the screen, just so that I can point at things on the screen and not be too small? Perfect. Okay, great. Okay, so this is more data than we were provided. There's a bunch of extra derived data, but essentially what we got in the data, we got an Excel sheet, two sheets on the file, and we got like an invoice ID, a code ID for the stock, some free text, the quantity, the invoice date, how much per quantity, and the country of the customer along with the customer ID. So we didn't get a huge amount of information in that data set. And this data set also had a whole lot of weird extra stuff as well that I talked about in other workshops, but we had kind of had to clean this data up quite a bit to kind of, there was refunds were in there, returns are in here, even though the original invoice isn't linked, and that was kind of causing issues. So I've kind of taken a whole bunch of kind of simplifying assumptions here. Now, in the normal circumstances, we would have someone to talk to about the data, and a whole bunch of questions came up about the provenance of this data, where it came from, and what things mean, which we don't have access to. So because this is kind of a virtual project, for one, or a pseudo project, I kind of made up some answers, and I kind of went with my gut or what seemed to make sense, or in many ways, what was easier for the purposes of this project. I had that luxury, so I used it, because quite often, you don't get that luxury, and there's certain realities of the project where you're not able to just make your life a bit easier. So in this case, I always kind of went for making my life easier, which is somewhat cheating in some ways, but in other ways, I don't really care. That's just the way it is. So the other thing, once we did that, then we kind of boiled things down. So we kind of aggregated the spend by customer invoice, and you can kind of, I have some code here, by the way. I've just put some code folding in, just it makes the code a little bit easier to read, to see what we're doing. So we've kind of, these are all the individual transactions. As you can see, there's over 1 million that were in the data set. However, once you clean everything down, and once we look at things, like I think these are customers. There was like 5,000, there's just under 6,000 customers. And for the purposes of what we're trying to do today, we often end up cohorting our customers based on when they first appeared on our system. So we consider the first transaction to be the birth of the customer, for want of a better term. And going off what I've read, you cohort your customers into different, cohorts based on when they joined the system. And apparently they can exhibit very different behavior depending on what cohort they're in. So your customer cohort can actually have a strong effect on, your modeling and your behavior. So I basically took the data, I'm not going to really, all this is done in R, but I mean, most of this, what I've done here, you could equally do just as well in Python, and possibly in some cases SQL. But I've just taken things like, take the customer, what was the first date that the customer transacted, that sort of thing. So having loaded the transaction data, I took some summary, so in invoice. So basically, by date and by invoice ID, what was the total spend? So ignoring all the different products that were bought, let's just look at what the total spend was. And for all of this stuff that we're doing today, we're completely ignoring products. We're not looking at all at what's being bought. We're just looking at how much is being spent. And that's kind of one of the simplifying assumptions that these models take. They don't look at any individual spending patterns in terms of what's being bought. It's purely monetary amount. Like when the transaction occurred, the fact that it occurred, and how much was spent, that's all that you really pay attention to. Everything else is kind of abstracted away by the model. And then we've a whole bunch of data that we look in here. So essentially what we're going down, we've taken all that data. We've also filtered out a whole load of kind of weird stuff, like I said. There is also a whole bunch of data in there. There was a whole bunch of transactions that did not have a customer ID. No explanation for that, but my gut suspicion is there is a mention somewhere in the data description that they also do wholesaling. So my feeling is that anything without a customer ID might be wholesale. And I did look, they did have some weird things, like some of the transactions that didn't have a customer ID would be very, very large in terms of both products and spend. So I've removed all of them. So it's only when we've actually got a customer ID And that brought things down to about 600,000 or 700,000. I can't quite remember how many transactions there were. And obviously, when you boil that down, you get it down to about just under 6,000 customers. And I think this is the invoice date. So I think it's per invoice. Yeah. So there's about just over 36,500 separate transactions, a transaction being the total spend of a particular invoice. So that's basically what we're going to do. So I've got a little bit of text here because if we're going to talk about the stats and stuff, I want to talk about kind of how this works. So the basic idea behind buy till you die is that a customer becomes alive to the business when it first transacts. So you kind of don't pay that much attention to the initial transaction. That's like the birth date. And then once the customer is alive on your system, the customer makes purchases at some predetermined rate, which is like a Poisson rate, if you think of it that way. And then eventually the customer will have a lifetime that customer will transact for, at which point the customer will die and no longer transact on the system. Okay. So your idea is that when you become, now this is a very simple assumption. It's a very simplifying assumption. We're not really accounting for any kind of different types of customer or any of that stuff. We're basically saying that you're born, if you think of it in terms of some kind of omnipotent being, the omnipotent being assigns you a Poisson rate and assigns you a lifetime, and then you buy at that rate. So stochastically, you're making random purchases with that underlying Poisson rate until eventually you hit your lifetime, and then you stop purchasing. You're dead from the system. And what these models try to do is they make some assumptions around those two like stochastic processes, and then they use the data to fit some models based on those underlying processes. So another way to think of it is you're given two rates at the start. You've got a rate of transaction and a rate of dropping off the system. So at every time step, if you want to think of it, let's say we think in terms of weeks, every week there's a chance that you're going to make a couple of transactions, and there's also a chance that you're going to die and no longer transact anymore. And that kind of process happens until you finally die, at which point you stop making transactions. And what we're going to do then is, based on those kind of relatively simple assumptions, we're going to basically take the data that we've observed and fit the models. Okay. So does anyone have any questions about that so far, about exactly like the underlying basics of this? Now, I'm very aware that there are issues with this model. Like, for example, the example I gave you before, where a customer only transacts for makes a bunch of transactions and then goes away and then makes another bunch of transactions, that doesn't fit this particular model very well, because that's not really a properly Poisson process. Because with a Poisson process, for example, or even negative binomial, it doesn't really pay attention to your history. Whereas in this case, it would depend on what time of year it is. There would be a whole bunch of extra things that you would need to account for. This model, it like simplifies all of that. It ignores it completely. And that's perfectly fine. Like I said, you want to have a simple model and you've got to start somewhere. And to me, that's what I like about this, in that, it's a series of very simple ideas that still ends up building a relatively sophisticated statistical approach to all of this. So yeah, so that's basically the idea. So I'm just keeping an eye on the chat, or by all means unmute yourself if you have any questions. Does everyone understand kind of the basic idea that we've got here? Now, we're not modeling at all customer births. That's kind of ignored from that. So like outside the scope of the model is new customers coming on. That's something you could do it, but you would have to model that separately, which is something you absolutely could do. But for the purposes of this, we're only paying attention to customers that are actually on the system. We're not really paying attention to the acquisition of new customers and modeling that particular part of things. So it's going to give you, for the purposes of like, even if you had a really, really good model that fit really well, that did a really good job of predicting all this stuff, it would still give you an incomplete vision into the future, because what you're not taking into account is exactly how new customers are coming onto your system. So it kind of ignores all of that. That's kind of beyond the scope of what. Now, like I said, I'm sure you could model that separately and then bring it into this, when you've got it in, and then you start assigning all that. And that's something you definitely could do. But for the purposes of this, we're ignoring it. Okay. So, all right. So basically, there's for most of what people care about, for what these bite and you die models done. This was kind of something that kind of messed with my head. Where most of the first part of buy till you die kind of ignores the monetary stuff completely. So we're ignoring how much gets spent on each transaction. All we're really modeling is the transactions themselves. So what we care about is how many transactions occurred and how frequently they occurred and how recently they was the most recent one. So that's kind of the recency, and the frequency. So ultimately, when we take all our transactional data, and this is kind of what I was trying to say here, and there's probably more maths and more algebra notation in this workshop than there has been in all the rest combined. We basically represent a customer with these three numbers here: this X, this T sub X, and this capital T. So X is the number of transactions observed in a time period T, which was the lifetime of the customer, and TX was the time of the last transaction. So we basically base everything off the time at which the customer was born on the system, i.e. when the first customer first made a transaction. We then counted up to whatever point in time we care about, how many transactions have been made since the customer came online. And that capital T is the time period observed since the customer was born, and TX is how far back in time was the last transaction. Okay. So essentially, we boil all that transactional data on a customer down to those three relatively simple summary statistics. So you essentially end up, every customer gets a row in a data table with three values in it: that X, which is an integer count, TX, which is the time since the last transaction, and T, which is the observed lifetime of the customer. Okay. And then we use that data is the input into the various models that we're going to talk about today. The two being the Pareto negative binomial and the beta geometric negative binomial. And they're essentially two ways of modeling the same thing. Okay. Does anyone have any questions about what I've done so far? No. Okay. All right. Okay. So this is one of those cases where I wrote out I wanted to be kind of explicit about these models, because it's very easy to get confused with these models. And also, one of the things I've noticed is there's a bunch of very good packages, both in R and Python, that do all this for you. However, if you don't really understand what the model is doing, I think it's a dangerous thing. It's a dangerous place to be. So I wanted to be quite explicit about the assumptions in the model and how they work, so that you can better interpret the output, because that, the assumptions in the model will affect how you interpret the output. And and I even found that myself. I didn't really understand what I was doing. I was just kind of playing around, and that's perfectly fine, by the way. When you're first learning something new, you should just play around with stuff and get a feel for it. But I wanted to understand the basic underlying assumptions and what's going on, so I could kind of get an anchoring in all of this and how this works. Now, there's two main models that people use. There's the beta geometric negative binomial, which is kind of the simpler to fit, and it's simpler to fit, and also kind of has a simpler implementation as well. But it's less powerful because it makes some kind of unrealistic assumptions about customer behavior, even allowing for the fact that buy till you die is quite a simplifying assumption. And I will talk about that in a minute. So the one I definitely prefer is and this was the first one, is the Pareto negative binomial. But they basically both take similar things. They have this model whereby it's essentially a hierarchical model, for those of you who have talked to me before about Bayesian stats or whatever. But the basic idea is that every customer gets a lambda, which is the underlying Poisson rate. Now, actually, before I make that assumption here, when I say Poisson distribution, does everyone understand what a Poisson distribution is and how it works? I'm going to quickly go over the assumptions of it, but it's probably worth mentioning. And just in case someone doesn't have it, do you mind just mentioning it in the chat? If you don't really understand what I'm talking about in terms of probability distributions. So the Poisson is like the simplest of the counting processes. So the idea is you have this underlying rate at which things, okay, excellent, thank you. All right, so essentially the Poisson model is about a simple probability, from conceptually, it's about a simpler probability distribution you can have when you're modeling discrete data. So when you've got like finite counts of things like nuclear radioactive decay or buses coming, or the amount of customers coming through a doorway, or the amount of customers on your website, or whatever it is, you generally have the simplest one and the most natural one to do is the Poisson distribution. And the basic idea is that it gives you the underlying rate. So that if we think of it in terms of time, your underlying rate is the average number of events that you observe in a unit period of time. So let's say, for example, our unit of time here is a week. If we have a Poisson rate of 1, we would expect on average to see 1 transaction a week. Now that's an average number. It doesn't mean a customer with a Poisson rate of 1 will transact 1 time exactly per week. You could have 5 in 1 week and then none in the next, right? So you'll observe it kind of that way. And so that number, it's a single parameter, just the lambda. So it's basically how often on average, what's the average number of claims. And the other thing to remember about the Poisson is it's a continuous value. It's bounded below at 0, so you can't have a negative Poisson rate, but anything from 0 to infinity. But the parameter itself is continuous, but the realizations of a Poisson is discrete. So if I have a Poisson rate, and actually that's probably a good thing to show. So if I do a Poisson rate here, which is R pos in R, so let's do 10 with a lambda of 0.1. Oops, misspelled. So you can see here, if you imagine that's 10 weeks, we had no transactions the first week, then 1, then 2 zeros, then 2, then 0, then 2, then 0, 0, and 0. And on average, if you did that, however many times, on average, you would get 1 per week. But, the individual realizations are going to change over time. And similarly, you could have, a lambda of 0.1, which means we'll have, we never saw any transactions at all, even though on average, we should have had 1. Okay? Does that make sense, Finton? Perfect. Okay. So what we're assuming here is that the customer will transact at a given Poisson rate. Okay, so if we think of it in terms of generative modeling, i.e., let's say we were going to make some synthetic transactional data, which a guy online actually did as part of this. And this is, in the next series of workshops, we'll probably do this. But if you think about it in terms of how do I generate transactional data that's according to a BTYD model, you basically have the customer gets a Poisson value, which is the rate at which that customer transacts. And then let's say it's on a weekly is your unit of time. You would say, okay, there's going to be 0 transactions this week, and there's going to be 3 in the next week, and then it's 0, and then it's 1, and then it's 1, and then it's 0, and then it's 1, and so on. Okay. So that's kind of the transaction rate for the customer. However, we're not saying that every customer is independent of one another. This is where the hierarchical model comes in. And this is the bit that I think was quite clever and kind of got me interested in the model, because I love hierarchical models. We then say that the population as a whole has a probability distribution, which is a gamma distribution, which I will explain probably after the break. But you've essentially, those lambdas are, each customer lambda is not independent. Those lambdas are derived from another probability distribution. So you can kind of think of it as 2 levels. You have a probability distribution that's determining each of the individual lambdas. And then once we get down there, in terms of that lambda is used to generate all the individual counts. So essentially the idea is that all the customers of the system are essentially informing each other on how they kind of behave, if that makes sense, because all the different customers will have different Lambda values, but those Lambda values aren't independent. Those Lambda values are all part of another probability distribution that sits on top of that, which is a gamma distribution. And we also estimate the values of that gamma distribution as well. So not only are we estimating the Lambdas for each individual customer, we're also estimating parameters for this hyper probability distribution. You might heard it as hyperparameters. So it's kind of like a hyperparameter because it's kind of controlling these. So if you think of it in terms of, again, this omnipotent being or generative modeling, if we have a brand new customer on the system, we pull a Lambda from this gamma distribution, we assign that Lambda to the customer, and then that customer uses that Lambda to dictate how many transactions occur every week. Okay, and that's our kind of our transactional part of the model. Now, the reason why it's called a negative binomial distribution, even though it's a Poisson, is that if you have that kind of model where you have a gamma distribution dictating a Lambda, and then the Lambda is using the Poisson counts, that actually creates what's called a negative binomial distribution. So it's an alternative way of creating the negative binomial. There's two different ways you can think about it. One is to think of it as this kind of hyper distribution, and the other way is to think of it as basically two parameters. You've got the thing, and you've got the Lambda, and you've got the mean or the dispersion parameter. I can't remember off the top of my head, because I use negative binomial because one of the problems with the Poisson is it has only one parameter, so the variance is determined by the mean. So in reality, the Poisson often doesn't do a great job of fully capturing the dispersion in the data because it's kind of tied. The variance and the mean are the same. So the standard deviation is just the square root of the mean. So there's no second degree of freedom to fully capture the data. And it means that sometimes the Poisson model won't quite capture the full spread of values. You know, you'll have things are too tightly wrapped around the mean. Okay. Oh, no problem, Jonathan. Okay, so does anyone have any questions? And that's basically why it's both the models are called the negative binomial distribution. That's where the NBD of both the beta geometric and the Pareto come in. So does anyone have any questions about what I've said there? Let me just go back to the model, and we can kind of see that in here. So we're basically saying the number of transactions made by a customer follows a Poisson process with transaction rate lambda, and heterogeneity in lambda follows a gamma distribution with shape parameters R and alpha. So we have, these are kind of like the population. The lambda is there's one lambda for each customer, and all those lambdas feed in to this gamma distribution that has parameters R and alpha. Okay. So does anyone have any questions about
that? Can I have a question?
Yes, shoot.
So can you check visually that the data has one kind of distribution, like you calculate some kind of lambda for all the customers, and you create a histogram, and can you see that, okay, the model will be fine for this this data set?
Yes, you can. That's what that is.
Okay.
Then you saw it on LinkedIn. That is an important thing to do as part of a data validation thing to check. From the purposes of, like, to use a technical term, even though I'm misapplying it here, like the goodness of fit. If you're looking for model validation, that's one of the things you should definitely do, is check to see, okay, well, if I take my distribution of lambdas, which my model is estimating for each customer, and then if I take the hyperparameters, this R and alpha that I have up here, okay, well, if I simulate from a gamma distribution using these two parameters and compare them to what I've got here, how well do they fit? Now, what you will find is generally that, you know, you get real life tends to be less. So you can see here the transaction rate. There's a smallest number of transaction rate that the gamma isn't captured. Now, that could be due to the fact that there just isn't enough time. We've only got 2 years. So the lowest transaction rate we could possibly observe is essentially 1 in 100 weeks, so it's 0.1. So that kind of makes sense why the data here in the black, and I'll talk about this more after the break, but you've kind of got this lower observation here. So this data down here isn't necessarily a problem with the fit. It might be just that we've got censored data due to the fact that we've only got a window of 2 years. So by definition, a customer can only transact once. Like 0.01 is the lowest kind of observed frequency rate we can observe because we've only got 100 weeks in our data set, if that makes sense.
Yeah, thank you.
Yeah, no problem. Okay, so that's kind of the transaction side of things. So we've kind of got, so what the customer is alive, doing the transactions, observing. So from a modeling point of view, we can probably see how that's going to work. We're basically going to focus on this X part, and essentially we're going to try and fit all those count values for the different individuals, and then we're going to also kind of feed that up into this gamma distribution that's going to feed the lambdas. All right, and you know, we can essentially fit both at the same time based on the data we've observed. Now, I'm probably going to take a break there because it's 5 to 8. This is, and like I said, rather than pick a particular time, this is a good place to stop. So it's 5 to 8 now. What I'm going to do is take a break for a couple of minutes. We'll be back at, say, 8:05. I'm going to run off very quickly and take a quick bathroom break. I'm going to turn off my video, but if there's any questions, please put them into the chat and I will mention it. So is there an interpretation of the Y of the gamma distribution? I'm not quite sure what you mean, Morgan, but perhaps we could capture that when I come back from the break and we can discuss that, because that's a very good question. There's a couple of ways to do, there's a couple of Ys there. The obvious one, being glib, is in most cases, you choose the one that makes the maths the easiest or is the most kind of natural fit due to the way things work. And the gamma and the Poisson, there's actually quite a close connection between the two, which I will explain when we come back. And that's probably why they use the gamma, although the gamma does also capture the right skew quite well as well. But yeah, we'll talk about that when we come back. All right, so here's what I'm going to do. I'm going to stop. I'm not going to stop recording, but I will turn off the screen share. If anyone has any questions, please just stick them into the chat, and I will put myself on mute, and I'll be back in like 2 or 3 minutes, and I can address any questions people will have in the break. All right, talk to you in a minute. Okay, I'm back. If anyone has any other questions, I'll address that gamma one once we're back properly. But in the kind of 5 minutes that we've got, if anyone has any other questions, I'm happy to address them now. Yeah, turn my video back up.
Hello, can you hear me?
Hello.
Ah, yes. Sorry,
Yes.
I wanted to ask the question directly. That's easier. So basically, I checked quickly the gamma distribution is used for population over a long period of time. Is there a way to interpret that as there is the number of people is there because publicity, when there is more people, there will be more people at the same time? Or is there some general model on internet buying that work there? Or
So the gamma, okay, there's a couple of ways of thinking about that. The most obvious reason I can think of for the gamma being used for the Poisson is because there's a very natural kind of mathematical connection between the two. So in Bayesian statistics, essentially they're called conjugate priors. So essentially, if you have a Poisson distribution and its conjugate prior is the gamma distribution, then you can, and you're trying to get inference about a Poisson rate, the data, you can combine the prior value, the prior parameters of the gamma distribution with the observed data in a very nice way that gives you another gamma distribution. And it kind of, so it's a very kind of mathematically quick way of doing that integration. And also another way of interpreting the gamma. I tend to interpret the gamma in terms of the Poisson. I don't want to show that right now because I want a couple of people to come back. But basically, the way you can think of it, and just one sec, I realized I haven't plugged in my laptop. The way I think of it is in terms of you can think of kind of the gamma as capturing the uncertainty in your estimate of your lambda in your Poisson distribution. So I would say from the point of view of why it's used in this particular model with the gamma, that is the main reason for that, because when people are kind of doing this kind of hyper distribution, like these hierarchical distributions, the gamma and the Poisson are just a very natural fit for one another. I don't know about, like, what it doesn't capture is those, I'm not sure, those kind of clustering of transactions and stuff. I'm not sure how well that works. It's possible. I just wouldn't like to comment on that.
okay,
My
thank
gut
you very
feeling
much.
is it doesn't, because ultimately, no matter what you do with the gamma, you're still going to have a Poisson underneath, and the Poisson is kind of a no memory, so it doesn't, like, there's no path dependency. So in terms of, it doesn't care how many previous counts have occurred. The next one is always independent. Like, the time for the next one to occur is independent of all the previous transactions. So there's no path dependency there at all. So whereas to capture that clustering, you would need that kind of interdependency there. So you would need some way of saying, I've just had a transaction, so therefore I'm more likely to have another transaction. And the Poisson doesn't really capture that. You would need probably some other form of prior or some other way of modeling that, if that makes sense.
Yep, thank you very much.
No problem. Yes. So essentially what happens is, if you're trying to get inference on a Poisson lambda rate and you're using gamma as your prior for that, and you have some kind of, and I'll talk about that once everyone's back in a couple of minutes. I'll show you a couple of plots. This was the way I started to understand the gamma distribution. It helps me kind of understand what the parameters do and how you interpret them. Kind of similar for where you would do a beta distribution with a probability. There's, if you can think of, if for those of you who are familiar with a beta distribution and say the binomial model, there's a very kind of, there's a strong analogy between that relationship and the relationship between a gamma and a Poisson. Before we move, yes, well, that's basically myself and Pedro, one of the other fellow organizers of Dublin Data Science. One day we both kind of had the day off, and because we're nerds, the two of us went to library bar in Dublin, for those of you who know it, in the Central Hotel, and we basically went on Wikipedia and tried to figure out what the hell the different parameters meant. And it involved basically a whole bunch of GG plotting of using various different parameters to try and figure out how things worked. So that's why I generally use the shape and the rate, because you could use the shape and the scale, but the scale and the rate are the inverse of one another. And to me, it's just more natural to use the shape and the rate. And I'll talk about why that is in a minute or two. Before I start back, does anyone else have any questions though? No? Okay, all right, so let's start back. All right, so let me just illustrate that. So the way to think, so we've got a gamma distribution, and this, so let's say we want to produce, let me, ggplot plus geoline. No, let me do it histogram, probably easier to, for the purposes of illustrating this. So our gamma, so we're going to generate 1,000 random numbers. Shape equals 1 and rate equals 1. So the way to think of this, the way I think of the gamma is, if you think, you can think of a Poisson rate. If I think of it in terms of a Poisson distribution. So if I'm observing a certain number of events in a certain period of time, how much confidence do I have in that underlying Poisson rate? So this is a very kind of Bayesian way of thinking about things, but that's typically the way I do things. So say, for example, and the way I look at that is, the shape is the denominator and the rate is the numerator. So let's say, for example, we go with shape 1. Let me just make sure I've got that right. Yeah, I do. And hold on, let's go with the bins there. Bins equals 50. All right. So if you see there, we have the shape of 1 and the rate is 100, right? So basically, I've got a mean of 0.01 and it's distributed around that value, but there's quite a bit of uncertainty, because even though, you know, I've done 100, I've observed 100 units of time and I've seen one event, so I'm fairly confident it's 0.1, but it could also be 0.2 or 0.04, I mean, but it's probably not 0.1, right? Because just that, you know, that just seems quite unlikely. And so the other way to, so if I think of it that way, but as these numbers, so what, in terms of the mean, the ratio of the shape divided by the rate is kind of the mean of the distribution. And the higher the numbers are, the more confident I am that that's the number. So let's say instead of making it 1 and 100, let's make it 100 and 10,000. So now you can see it's much more tightly distributed around 0.01, because these numbers are higher. Similar, if I was less certain, I would go, let's say 0.01 and then 1. And now I've got lots of uncertainty in my underlying Poisson rate, because the Poisson rate, you know, even non-zero, like values greater than 1 are possible for the Lambda, because I'm just very, very uncertain about how much I've seen. So you can kind of think of, if you think of it as a mean multiplied by a number, the rate is like your strength of belief. You can think of it kind of like the precision, the inverse variance. So the strength of belief is the rate, and then the shape divided by the rate is the mean of the distribution. And obviously, the higher those numbers are, the tighter it is around the mean, and the smaller they are, the more uncertainty you have. And because it's got this right tail, it's not very heavy tailed by any means, but it does have this kind of right skew. You can also capture these kind of higher values. They have essentially a non-vanishingly small probability of occurring. Now, it's not a very heavy tail distribution, but you do kind of observe, you know, a right tail on it. It does have so you do get this skew on it. Okay, does that kind of make sense? I'm hoping it does. So that's why the gamma is a very good fit for the Poisson, because you can very naturally think about, like if I'm thinking, okay, I want a gamma distribution around this uncertainty, Okay, so I'm going to set my gamma prior. This is, again, I'm getting Bayesian here. I'm conscious of. Oh, someone's talking there. Oh, right, okay. Okay, so the gamma there is a very natural fit for that. So we kind of have this gamma distribution feeding into a Poisson distribution, and that gives us our negative binomial model. So that's where the NBD comes in. Now, and that there is the same for both the Pareto negative binomial and the beta geometric negative binomial. Now, where they differ is on the lifetime process. So as I remember, there was two parts of this model. There is the transaction process and there's the lifetime process. Okay, so the Pareto distribution, the PNBD, which was the first one that was created, I think it was 1987, the paper came out. They have a similar process. So you have basically a lifetime of length tau, at which point the customer becomes inactive. It's distributed as an exponential with dropout rate mu. So again, you can kind of think of the dropout rate mu. The exponential is kind of the alternative way of looking at a Poisson. If we think of a Poisson as for a fixed given time, how many transactions do we observe in that fixed unit of time? The exponential is the inverse of that. It's that what's the distance between, like what's the length of time or the length of whatever unit we care about between events. That's distributed. If you've got a Poisson distribution, you will have an exponential distribution with the same parameter, but between the events occurring. Okay, so again, so the two ways to think about this is you can think of it as we're assigning a lifetime, the full lifetime of the customer, as being an exponential distribution. Or the other way to think of it is that for every unit of time, there's a dropout rate. That customer, similar to the transaction rate, there's a chance that the customer will drop out, and as soon as that occurs, the customer essentially dies and ceases to transact. Okay, and that is similarly, we have, before we had a Poisson distribution with a gamma above it. Now we basically have we have an exponential lifetime with an exponential distribution with a gamma above it. Okay, similar to that, and that creates a Pareto distribution. It's technically a Pareto distribution of the second kind, apparently. Now, I'm not fully au fait with the various different Pareto distributions, but essentially what happens is, because you've got this exponential distribution, which again is governed by a single parameter, which in this case is the mu, but we've put a gamma prior on it. I think what happens is, because you've got this right tail on the gamma and you've got this right tail on the exponential, you essentially get heavy tails. So you can essentially have very, very long lifetimes for customers. You can have customers that will have, normally will have very short lifetimes, but you do have this long right tail. So you'll have very, very long-lived customers according to this distribution. And that's why it's called the Pareto negative binomial. Even though it's a Poisson and an exponential at the customer level, because we have this hyper distribution of a gamma for both, it's a Pareto negative binomial. Okay, and as a result, as you can see, basically there's 4 parameters we fit. When we're doing the overall model, what we're fitting are the 4 parameters of the gamma. So the alpha R for the transactions, and the S and the beta for the lifetime process. And essentially when you're doing PNBD fits, you're fitting those 4 parameters. Now, the problem with this is, and I've kind of mentioned it here, I found that not as useful as, another very important, a key assumption of all this is that there's independence between the lambda and the dropout rate. So you don't have any actual correlation between, say, or dependence between the lambda, the transaction rate, and the dropout rate mu, the lifetime. So the lifetime and the transactions count are independent of one another. They don't correlate, or they're not dependent on one another. And I guess that's one way you could extend the model. If you have essentially, the classic, burn bright customers who die young. So you could have those customers that come, they buy a crap load of stuff and then they lapse off your system. Or you could have these customers that don't transact very often, but they last for a long time. And if you needed to somehow build in that dependency, you can do that. It becomes a different model, but that would be a way in which you could extend the model if you wanted to. Okay. Now, we do have a problem with the Pareto negative binomial, even though for me, it's the more intellectually kind of coherent value, because you have problems fitting the model for various reasons, and there's various reasons given. But I've always been a long adherent of what's known as the Folk theorem of statistical computing, which is that if you have problems fitting your model, it's not a computational problem, it's a statistical problem, as in you've got a problem with your model that you probably need to change to fix it. So Andrew Gelman's a big proponent of this. He says, like, numerical computation issues are usually modeling issues in disguise. So I think what might happen is when you're trying to fit these distributions, and the data we have when we try to do this, we do have modeling issues. That the Pareto PNBD doesn't fit very well, or at least I've had trouble with it, and that tells me that we're doing something wrong, or the underlying assumptions of the fitting are problematic, and that's something why I want to do it in Stan, because that allows us to kind of hit those head on. But in the meantime, basically, a lot of people use what's known as the beta geometric negative binomial. So they do the exact same thing for that, but they make this other simplifying assumption that basically customers don't get a lifetime. Instead, what happens is they every time they make a transaction, there's a fixed probability of the customer, fixed probability for that customer of that customer becoming inactive. So as soon as they make a transaction, essentially they check to see, am I dead? And if they're not dead, they live to do another transaction. But if they are dead, they stop transacting. Okay. So at some point, basically they transact. And at some point, especially if it's, even if it's a relatively low probability of churn, they churn at some point and they stop transacting. Now that has, and again, similarly to the PNBD model, the transaction rate lambda and the dropout probability P vary independently across the customers. Now, the reason why that's called the beta geometric is you model the probability using a beta distribution, which is A and B, two shape parameters. You can kind of think of it as roughly how many positive tests and roughly how many negative tests gives you your probability. Is a kind of a quick way of thinking of it. And then they transact each time, but because of the Poisson process of the rate, right, their lifetime now is kind of related to their transaction rate, because how often they transact will dictate their lifetime, and that's why they have this geometric distribution, because it's basically probability P, and there's this repeated trials over and over again in between transactions. So even the probability P is independent of the transaction rate. The lifetime no longer is. And the other problem with this model is that it means that your very loyal customers who transact very frequently, you're going to underestimate their probability of still being alive on your system. Because they transact so often, they're just making more tests to be alive, if you think of it. So if you think of it going forward in time, your forward estimate of the probability of customers being alive 3 months into the future is going to be lower for your really loyal, for your most active customers. So that's something you kind of have to be aware of. However, it's very easy to fit and build this model. And I believe one of the reasons why the beta geometric, the BGNBD model got so popular originally is you could literally build it in a spreadsheet. So you could take the data, you could create, the triplets, the X, T, X, and T. You could fit your model and you could do it in a spreadsheet, and you would immediately start to produce relatively simple results. Now, I'm not going to go into the various, the likelihood models of this. That's all done in a package called CLV tools, and also the BTYD and BTYD plus tools. I'm going to ignore them for that. I'm just going to kind of focus on fitting them. However, one last thing I'm going to talk about, because I am conscious of the time, is the spending model. So we also have what's called the gamma-gamma spending model. So we haven't talked at all at this point about monetary transactions, which is kind of like a missing piece from all this, because even though we know that a customer is transacting, we also want to know how much they're spending, and it would be good to get some sense of how that model works. So there's also, on top of kind of the BGNBD or the PNBD models, we also have what's called the gamma-gamma model. So in that case, basically, we say that when we're looking at all these transactions, we look at the monetary amounts and we say that every customer has a gamma distribution that dictates the spend. So for any individual customer, we have all these different transaction amounts, and those are distributed according to a gamma, this P and U. But then this P, which is the shape parameter of the gamma, also has a hyperparameter, Q and gamma, little gamma, right? So we end up essentially with 3 parameters in this model, because we have the nu for each, which is a constant across all the customers, and then we have the shape parameter dictated by these Q and gamma. So we can also fit this gamma-gamma model. So it's a gamma at the lower level and a gamma prior dictating the shape parameter. Okay, so I know it takes a bit of getting your head around, and that way we can also, once we've kind of got a feel and estimates for the various parameters on the recency and frequency side, we can essentially overlay this gamma-gamma side. And CLV tools kind of does that for us. Now, I looked a little bit at BTYD, like buy till you die, and they have a couple of nice, like, you know, they have, this is the customer counts at each transaction. So you can see, you know, and you can kind of see it actually kind of follows it's like an exponential decay across the different transactions, which does lend a certain amount of credence to the beta geometric, by the way, because you can kind of see there is kind of a nice kind of exponential curve dropping off. And I do know some people have used this on real data, and they've used the BGNBD and it's fit their data really, really well. And they were more than happy, and they just didn't bother looking at the Pareto NBD. They just went beta geometric and fits my data. I can make predictions, and I'm very happy with the prediction. Now, of course, like everything else, there's not much you can do to very new customers. All you can really do is look at kind of how much spread there are and make projections about what they're going to do. But you won't get a good sense of what that's going to be until they start making a bunch of transactions. So that's kind of the one downside to the model, but it's not so much a downside to the model, it's a downside to the very sparse data that you often have on customers. You know, they come onto the site, they make a couple of transactions, you might not have a good sense of it. I guess that's one way you could, if you're starting to build fancier models, you could start to build in what products were bought, and that would allow you to segment your customer base and bring that segmentation back into your model and build up a hierarchy that way. You could probably do something like that, but you're kind of going beyond the simple model that I'm just trying to focus on here. So yeah, so it does all that. So you can see we've this heterogeneity in the transaction rate. So this is kind of the model that we've fit. So you can see this is kind of the distribution of the various transaction rates. Let me just get my mouse. So you can see, you know, it's following that kind of, this is the right-hand side of a gamma. And we similarly, for a dropout probability, we can see we kind of, you know, it drops out there. But on this, I'm going to quickly use CLV tools. So I'm not going to worry too much about the data here in terms of the modeling and the R code. I don't really want to kind of get people confused by, you know, the various coding bits, because to be honest, like I said, I always try and make this as code neutral as possible. But, you know, what have we done? You know, the data actually provides some data we've to pass. Now, one thing we do have to do, the data doesn't manage essentially customers that have not, so we're going to create a training set and a validation set. So we have this cutoff point of as I said, the data goes from kind of the end of 2019 to 2009 to the end of 2011. We have a kind of a cutoff point of our input data or our training data to be the 31st of March 2011. So we kind of leave the last 6 to 9 months or so for validation purposes. So we exclude from the data set any customers that had their first transaction after that customer point. Some of the data, some systems automatically exclude them. CLV data doesn't let you, and I think that's better because, you know, you're removing, rather than silently removing data and not really telling you, it's better to just fail noisily and tell you why, so that you can fix it, so that you're kind of more in, the less the computer does on your behalf unknowingly, the better, because that's, you know, that's the path to madness. That's, you know, that's an easy way to lose a month, because you know the computer is helpfully doing something for you and not telling you, and you can't figure out why, and it's messing up something further along, and you can't figure out why, and you go a bit mad. That's happened to me loads and loads of times. So I was very, very glad. And BTYD and BTYD Plus takes those data out silently, whereas CLV data doesn't. And they kind of talk about a bit that in the notes. So, oh, and sorry, I should point out, just for the purposes of this project, I had to learn all this for this project, right? And that was one of the motivations for me to be doing these workshops. But you know, I didn't know this in advance. So part of this did involve just going on to the BTYD packages in R, you know, and Googling stuff and Googling blog posts that explain some of the underlying code. I have found some of the underlying theory here is probably not as obvious as it should be, because they're like academic papers and they drown you in a bit of algebra and likelihood models and doing the, you know, the derivations of the formula. And sometimes you kind of lose sight of what's actually going on. And that's one way in which the web is brilliant, because you'll get a bunch of blog posts. If you Google like BTYD or customer lifetime value or something like that, you'll probably find a bunch of good introductions to it. And I'll see that in the lists. What I might try and do up the top here is share a few links, and I will add them to this. But this kind of gives it, so you can see, you know, you put the cutoff point in here. This is all kind of summary data from the package. So you can see we're estimating from the 1st of December 2009 until the 31st of March 2011. And our holdout set is basically from the 1st of April to the 9th of December. And, you know, we've got some various summary statistics in there. And then we've put our cohorts in, and we're going to fit the beta geometric NBD model, and we're just going to fit the parameters. So we have, as I said, we produce 4 parameters from this. We have the R and the alpha, which is the gamma distribution for the transaction rates, dictating our underlying Poisson, and we can see they fit very, very well. And then we also have the A and the B, which is the beta distribution. So the way to think of the beta, can I make an assumption? Actually, I should probably ask, I know people aren't aware of the Poisson. Are people aware of what a beta distribution is and how it relates to probabilities in the binomial model or the Bernoulli model? Does someone want me to quickly explain what the beta distribution is? If not, just put something in the chat. Everyone's gone very quiet. All right, so, okay, a quick explanation. All right, so I mentioned earlier about the Poisson and the gamma, and kind of it measures your uncertainty. The beta distribution is very similar, and again, I can go back to R to illustrate this. I love illustrating things with a. So if I think of R beta, so the R beta is, it produces a number between 0 and 1. You can think of it as a probability, and I think it's shape 1 and shape 2. But the way to think of it is, if you think of it as binomial trials, so tossing a coin, how many positive events did we find and how many negative events did we find? And the beta then gives us kind of a distribution of the probability uncertainties. So let's say, for example, let's say we've got some binomial trial and we do 10 of them, and we add 1 for mathematical reasons. So let's say we have 10 positive and none negative. Well, then we're pretty certain the probability of the event is 1. Now, it's not directly 1, although it could be, but there's also a chance that we've just gotten very lucky, and the probability, you know, it's almost certainly not below 0.5, because, you know, we've done, if you think of it as 10 trials. So that's what, and we have to add the 1 for mathematical reasons. It's just kind of the way to think about it. But similarly, let's say, for example, let's say it was 50-50. So we'd had 5 and 5, right? Well, then if we go 6 and 6, because it's 5 plus 1 and 5 plus 1, we get this kind of, you know, nice symmetric distribution around 0.5. So if you think of it in terms of Bayesian updating, the amount of positive examples gets added to shape 1, and the amount of negative examples gets added to shape 2, and that becomes your new beta posterior. So in a beta distribution, you can kind of think of it that way. So if you were to put some kind of distribution around what we expect the probability to be, the beta distribution is a way of modeling probabilities. It's probably the most natural way to do it because, again, it's the conjugate prior in the Bayesian. Now, I don't really want to go into that too much, and similarly, but again, the numbers of these is like the strength. So let's say we went instead to 1,000 and 1,000. So let's say we had 1,000 and 1,000. Well, then we would have 0.5 is our midpoint again, but it's going to be much more closely packed around the 0.5. Do you see that? So now anything even below 0.46 is very, very unlikely. So the probability is almost certainly around 0.5 now. It's not going to be very close to 1, and it's not going to be very close to 0. In fact, it's not even going to be moderately close to 1 or moderately close to 0. It's going to be close. You know, the data is telling, because what that corresponds to is having taken 1,998 tosses of a coin and gotten exactly 999 heads and 999 tails. So the more times you do that, the more strength of belief you have in what the underlying probability is. And that's kind of the way to think about it. Does that make sense? So here we have here a beta distribution of A and B. So it's 0.14 and 0.428. So what that is telling us that the probability of survival is very close, is high, which kind of makes sense, right? Because the P is the probability of surviving, I think, if we just look at the model. So hold on, where are we? Up here. Becomes inactive with probability P. Sorry, so it's going to be very low. Of course, B is failures. So when we look at the B here, we can see the B is much, much higher than A. So that suggests that the distribution is shifted towards the right-hand side. So actually, let's plot that. So we've got what, 0.14. The beta is 0.14. And the A and B are both positive numbers. So any value greater than 0 is a valid input to these probability distributions. So we've got 0.428. So we can see here, yeah. So if you think of this as the transition, like the drop-off probability, the likelihood after any given transaction of a customer dropping off is relatively low. Now, some customers will still get high probabilities, right? Because they'll drop off very quickly, and that's absolutely fine. But in general, most customers stick around for a while and then they drop off. Okay, so that's kind of what the model is telling us. And then, you know, we can do a tracking plot as well. There's a bunch of things. So this is kind of the overall number of repeat transactions versus what our model is predicting, I think. Oh, sorry, yeah. So if the model was completely accurate, the red line is what we would observe, whereas in reality, this is what we've seen. And now we can check for model fit. So this goes back to, you know, what we've looked at before. So in the previous thing, we had transaction rates. So I've taken the output for every single parameter, for every single customer in the data, we're predicting a lambda, which is the transaction rate, right? And then those lambdas are all drawn from the same gamma distribution, if you remember, and that was dictated by R and alpha. So what I've done here is I'm basically taking those parameters to predict. So this is these are realizations from the gamma distribution according to the values we dictated. So using the R and the alpha. And then these here are what we actually observed. So these are the lambdas according to our model, right? So, I mean, is it a great fit? No. I mean, to a certain extent, like I said, we have censored data here because there's only about, if we scroll back up here, and this is something to be aware of, like our estimation, we only have how many weeks our estimation period had 70 weeks in it. So the lowest observed frequency we can realistically have, because we're only going to count customers that have made repeat transactions, remember? We've gotten rid of any customers that have only had a single transaction and never, in terms of the transaction rate, as a result, our kind of minimum is 1/70, which is about 0.14, I think, right? So 0.14 is kind of the lowest, sorry, 0.014. So that's the lowest we can kind of observe, and we can see that, down here, that's roughly e to the minus 2. Well, it can't, Neil. It can't from the observed value. If you know that, like, we're not dealing with distributions here, we're dealing with point estimates. So it does take account in the sensor data, but it doesn't change the fact that because we've only got like 70 weeks worth of data, we can't really have an estimate below that minimum value. If that makes sense.
Yeah. Well,
So
what you're saying is it doesn't really do sensor data properly, or you can't set it up. Even though it seems to be natural for the problem.
Yeah. So I could
look through the the what you call it or
you can't have, because the transaction rates only occur if there's multiple transactions, because it's the first transaction is born, and then you have a second one, so you need that second transaction. So you otherwise you just assume that the customer transacts and then dies immediately. So it's so you need the 2 transactions to get the estimate of the transaction rate.
Yeah, I suppose.
Because the first one isn't counted. The first one is just the birth on the system. It's the second one when you start counting for transaction rates. So that's why you've got this kind of minimum value. And that's kind of inherent in the problem.
Yeah.
But the single transactions are accounted for by the dropout rate. So in that case, what would happen is your customers who are just, by birthing and then immediately dying, their dropout rate is higher, so therefore their lifetime is very short.
Well, presumably, you don't actually know they're dead. You just know they haven't. They just have a very long transaction time.
What they have is a high probability of being dead, or a low probability of being alive. Yeah. All of this is entirely probabilistic. So, and that's actually something the models do. They estimate the probability of a customer being alive, like at the end of the transaction period, and that's one of the things you can estimate from the model.
Oh yes, then it does that.
And obviously, for those customers that transacted a long time ago and haven't transacted since, their probability of being alive is very low. Otherwise, because otherwise they just have a very low transaction frequency.
Yeah,
which is probably not in keeping with the other data.
Grant.
If that makes sense. So yeah, you're kind of into the same regions here for those of you who are familiar with it, with frequency analysis. When you're doing kind of Fourier, you've got that Nyquist frequency, which is the minimum frequency, which is like twice the minimum observed period. You're kind of in this, it's a similar kind of concept. You can't really observe shorter transaction rates than the full length that you've observed.
Yeah.
Because of censoring. Okay. And censoring can only do a certain amount for you. Okay. Any other questions? Now, and then similar, we can also go on to like spending models. So on top of all this, this is like the output. We can make predictions. So once we fit our distribution, this is all beta geometric. We can then start like making our estimates. So we've got like the actual X. We can also add in this particular package. You can basically add in the spending model. It automatically fits the gamma on top of the spending data, and it will tell you what that is. So you can see here, all these customers have a probability of being alive, and that is at the end of the training period. So you can see there's a whole lot of, so we can start looking at that. We've got a density of average transaction values, and we can look at the heterogeneity of the spending patterns. So we've got, the mean spending is calculated from the gamma distribution, and we can look at how that works. So we've got, a gamma. So again, we've got the underlying pattern of the customer rate versus what the distribution would fit. And you can see that essentially probably what's happening here is the data, there's probably either minimum spends or more likely there's more common spends that the model is not accounting for. So almost like we have a mixture model here. We have another way to think about this was some types of customers spend in a very narrow range. And I think if in previous values, if you remember, we looked at that and we did find spikes. I can't remember exactly how much it was, but we were getting these spikes at certain spending amounts. So it was like there was a very common amount of transaction value that the gamma distribution isn't really capturing. And that's what we're observing here. So we can see definitely there's issues with this gamma model, even in the spending patterns that we're not fully accounting for within that. But that's okay. I mean, it's like everything else. No model is perfect. The key thing is to know where it falls down and maybe what we can do to either work around those failings in the model or improve the model later. They all give us different things. So yeah, so that I mean, again, I don't really want to go into the modeling and the code there, because the code is all there if you want to fit it. I more want to give an idea of the overall approach. And again, I'll go into this in much more detail next year in my next set of workshops, because I think this is a very interesting kind of statistical model that you can get an awful lot of use out of, that can provide a lot of very valuable insights. However, as you can probably tell, teaching this stuff to a non-technical audience is going to be a challenge. And for the purposes of what I'm thinking, this would be the stage 2 of the project, where, you know, we're going to present some simple stuff at the end. That's going to be our final version starting next month, which was probably 2 more. I'm thinking we're going to have kind of in the next workshop, I'm going to have, here's what the model is, and then the final one would be like presentation and thinking about what we can do about that. I've just been thinking about, like, I'm even conscious as I'm explaining this to you guys who are a relatively technical audience compared to, certainly very technical compared to the target audience, like ultimately the stakeholders of this project. Explaining this is going to be a challenge to a lot of people, and they'll just see this as being magic. And I think you can get a lot more buy-in by explaining something that they understand and that they can do something with. That gives you the buy-in to then do the fancier, clever stuff later, if that makes sense. And this is why once I was doing this, I was going at this going, how on earth am I going to get some useful stuff out of this? I can do some predictions, but I would like to be able to present something very, very simple that people can understand. And I couldn't think of a very good way. Like, even how do you dictate what good customers are? I guess customers who transact a lot and spend a lot of money. So you could do some kind of scatter plot of average spend, but even then, you see, average spend doesn't help because you've also got this distribution of spends. So do you have a high average spend because most of your transactions are relatively small, and then every so often you splurge, and that shifts up your mean? And that would be very well captured by a gamma, right? But it's also not accounting for the fact of transaction costs. You know, if you've got to spend a lot of money, if you have a fixed amount of cost per transaction, then maybe that's not as good as someone who spends less money overall, but has less dispersion in their spending patterns and is higher up the chain. So, you know, we can deal with all that later. And from a modeling point of view, if you're going to do that, then you probably want to build those from a simulation or some kind of model output point of view. You kind of want to bring them into your model. You want to incorporate those concepts into your simulations so that you can properly assess who counts as a valuable customer and who doesn't. Because, you know, what you would like to be able to do is not just look at revenue, but also look at like profit or transaction costs or whatever, and build all those in. So like I said, it's not entirely obvious from this data here what counts as a good customer or not. Now, the other methods we talked about are much cruder, but at least they have the benefit of simplicity and they're easier to explain. So kind of once I went down this road and I was going down all of this, I kind of took a step back and went, no, for the purposes of what we're doing today, we're not going to use any of this stuff. None of this will be like in the final results that we'll probably mention it, that we did it, but you know, here's what we decided to pursue and why. But, you know, just moving on, because, you know, today is the day and I'm conscious we've got a little bit of time left. The other thing you do is we've kind of fitted the entire data set in one go. They don't recommend to do that. What they recommend you do is you split your data into different cohorts. So you basically split your data into multiple groups of data and you fit a different set of parameters for each cohort. Now, personally, the way I would like to do that is to then make that hierarchical. So you also have the cohorts as part of the predictive model. So, you know, they can all inform one. You can fit, rather than fit in multiple models, you can fit everything all at once. To do that, we would be going the Bayesian route, and that's something we'll probably look at in the next set of workshops. But, you know, essentially you've got different gamma distributions. Now, this is where things get a bit mad. You can see here that this cohort here in Q1 2010 has absolutely mental values for certain things. Like, look at this, alpha off the charts and an R off the charts. So there's something really, really weird going on with that cohort, and I haven't figured that out. I'm not sure what's going on there. That's something I actually want to kind of investigate. Now, if you look up here, we did some models. That is the wrong one. Oh, you know what? I've done this a bit different. I actually remodeled it, and I didn't use the remodeled stuff. So, you know, when we look at the model fit, investigate the spending models, I actually had some. Where are my? I had some nice. So yeah, so I don't really know what to make of that. What to make of this? I mean, look at these values; they're crazy. So there's something weird has happened there as well, and that just gives me the heebie-jeebies about this entire approach. And what I don't want to do is look like an idiot in front of a bunch of people who aren't very technical, because they're just going to go, "This guy hasn't a clue what he's talking about." So a combination of the model being complicated, these weird fitting issues on certain cohorts, and these aren't insurmountable problems, but it just occurred to me that the juice is not going to be worth the squeeze on this. So let's just ignore it for now. So yeah, but you know, you can do your splits. I wanted to look at this. I also went the bootstrap idea because I love bootstrap estimates, but bootstrapping these is a bit weird because essentially you're bootstrapping the transactions. And if you bootstrap the data for the same date, they all just get, all those different transactions in the bootstrap sample get combined into the same day. So you're essentially downward biasing your bootstrap estimate. So I'm going to need a better way of bootstrapping that as well. But I included them there again to show where things are bad. I think I actually mentioned it in a little bit of the text. Is everyone familiar with the bootstrap? Does anyone not know the bootstrap? So basically the idea is you sample with replacement, and you create different bootstrap samples of your data, and then you fit the same model in each bootstrap sample, and it gives you an idea of the error due to sampling in your parameter estimates. So it kind of gives you a distribution of parameters, and it gives you an idea of how, you know, how stable your parameter estimates are without going the fully Bayesian route. Although the problem is you end up fitting a lot of models, so it can take a while. However, I don't think just blindly sampling the data this way is the right way to go, because you, like I said, with the transaction rate, you end up downwards, you end up just getting bad estimates off it. Because if you randomly sample all your transactions for a given customer, then all those customers because we're using that summary data, all those transactions, it just ends up being one transaction with a much larger amount of money rather than separate transactions. So instead, what I think I should have to do is basically take samples of differences from points in time. So let's say, for example, I start the Sunday of every week, and then every customer has a random sample around those days, and then sample them with replacement and build up a transaction set that way. I think that might be a better way of building this, because that would more properly capture the data that we see. So I'm going to have to think about how exactly I'm going to do that. I haven't quite figured that out, but you know, the bootstrap, it doesn't always. So sample by customer, because I also want to get the sense of the customer, Neil, if that makes sense. You know what? Let's talk about that afterwards. Let me just wrap up, because that's a good point. I wouldn't mind, actually, for those of you who are here and have any thoughts on this, I'm trying to get a sense of, you know, I've got all these transactions, right? Every individual invoice. I would like some way of randomly sampling with replacement that data to give me like independent sets of data, but that when I aggregate them down, they don't all collapse down to the same date, so that I end up underestimating. properly capture the variance in the individual transactions. Because if I end up sampling, you know, the same invoice from this date 3 times in my bootstrap sample, they'll all collapse down to a single day and a single transaction. So I won't have 3 transactions in my bootstrap sample. I'll just have 1, but the currency amount will be 3 times bigger. So, you know, but I'm not necessarily modeling the monetary. I want to model the frequency. So how do I handle that? But that's basically, I'm going to leave it there because I'm conscious it's 10 to 9, and this is not trivial modeling. Like this is a reasonably sophisticated statistical model. I just wanted to give people a flavor for it. Hopefully you kind of understand now why, having spent a bit of time and effort like building these models and working on them and trying a few things out and seeing where I could go with it, I didn't really bring it to completion because it's just too complicated for what we're trying to do here. What we're trying to do is get a rough idea of customer segments and how valuable they are and maybe what products they buy. And while that would be useful probably for like customer metrics, I think it's just a bridge too far, and it would be something we would come back to in, like, if this was to be an ongoing project, the first part, what I want this project to be is the thing that buys you the credibility to do the more clever and useful stuff, having done all the hard work of doing the visualizations and doing the data building and doing all that kind of stuff. And I think this is the kind of type of trap you can fall into. And we've been in this. I've fallen into this trap personally a few times, where you end up in a meeting where you're talking about your results, not necessarily, you know, progress reports, and you end up discussing the finer points of how to fit a model. And it becomes very clear that the people you're talking to have no idea, even though they think they do, they don't really understand what you're talking about. And that's not a good place to be. So I would always like to do something simpler and you know, more like useful, but very simple, so that people can be happy with what you're doing. You don't make them feel stupid. You're not trying to explain anything. You're not trying to get into the technical details of a statistical model that are, you know, important to interpreting the nuance of the output. Well, essentially, you want to be in a position of trust where the person understands that they don't really understand the maths, but they trust you to get this stuff right. And that if they give you relatively high level questions, you can come back to them with, you know, sophisticated answer to those questions. And the way you buy that credibility is by presenting simple things first that make sense and you've done a bit of validation on. And I've already found, even just looking at the RFM models and a combination of grouping products and segmenting our customer base based on like last month's workshop and the RFM models we built there, that's more than complicated enough for what we're trying to do here. So I know this was a bit of a weird one in that, you know, I've spent 2 hours talking about a model that I'm not going to use, but one, it's important, and it's like, just to stress the importance, BGNBD and PNBD models are fit as part of various cloud suites now in their machine learning archives. So like, I think Amazon and Google and probably Azure, but I can't speak to Azure, but I'm almost certain, I know for a fact Google does, because I use Google Cloud, and I'm almost certain Amazon does that. As long as you put like the transactions into like BigQuery or DynamoDB or the various data solutions, and it's held in the format that they ask for, you can automatically fit these models as part of their machine learning suite. They're like features that they add as part of API calls. And they, you know, they have inbuilt libraries that will fit all these for you. Now, I'd still be a bit wary about using them because of all the issues that you've seen here in terms of trying to fit these. And I didn't even talk about the problems I had with Pareto NBD, where they were just completely unstable. And like, we've got that weird cohort issue with the beta geometric NBD. So yeah, I think they're really powerful, and I can think of a bunch of different applications for them, like in banking and brokerage and a whole bunch of other things where these things would like make sense and be useful. But like I said, we're not going to use them now. I'm going to return to this a little bit later. Oh, okay. Yeah, it's part of other things as well. They're just kind of inbuilt. Presumably, certainly, whatever about PNBD, BGNBD definitely will be, because it's so easy to fit and you get reasonably good fits, you know, as long as your data isn't totally pathological. and it's very quick and fast to fit, and you get useful outputs from it straight away. So so we're going to leave it there. So I'm probably going to run a workshop next month, even though we have a talk. We have a talk next month, which is great. Now we're not using Crowdcast anymore with Dogpatch because they no longer have Crowdcast because they just switched to Zoom. So we're just going to use Zoom from now on. We have a speaker from a friend of mine from London, a guy called Simon Sonkala. He is talking about boosting. The date is set in Meetup, but I haven't added any details yet because I'm still waiting for him. And we have an attendee tonight who had to leave earlier. Jonathan Adams is going to talk about Monte Carlo simulation and Arminians and asynchronous jobs and job management and all that kind of stuff. He's going to talk about that in October. So I think I might double up next month because I'd like to finish this. And I think if I could just go like September, October, because I think there's two more. I think there's one more, which is going to be like taking all this work, figuring out what we're going to present to the client and present it. And it's basically going to be some clustering of the products based on some graph models and association rules. That's the first one. And on the product side and on the customer side, we've done some customer segmentations using these RFM models, like we discussed last week or last month. Combine the two in a bit of maybe correspondence analysis to get a sense of what, like your champions, your really good customers, what kind of products do they buy and what kind of products maybe don't they buy, that sort of thing. And that I think will give us, a decent set of results that we're going to present. And then the final episode, the final workshop is just going to be thinking about ways in which we present our results. And it might be, I haven't actually thought about that yet. I'm thinking I might build a simple Shiny app. I'm not quite sure why or what. We won't really talk about building Shiny, but I would like to point out that it's possible, or maybe do some interactive widgets on a spreadsheet. But ideally, rather than just presenting them with a whole lot of facts and figures, it's nice to give them a tool that they can play with, because that's a really good way of getting buy-in. When people can like change things on a slider or type in something or select something from a drop down and like click a button and get the results of what they're looking for in the screen, that to me is a really, really good way of getting buy-in for the work that you've done. Whereas presenting people with just page after page of charts, no matter how pretty they are, people just don't really like that. So we're also going to have a little bit of a think about how we can present all our results and what we're going to say and how we're going to say it and like what our key takeaways are. So what we want to be able to do is have, a simple answer to the question of what were the results of the project. And I would like to be able to say, well, we found that our most valuable customers tend to buy these products and don't buy these products. If we could say that at the end of this project, to me, that's a way that's what success looks like. Or have, here's a list of products that maybe we shouldn't sell anymore, or customers churn if they buy them, or, there's all sorts of different things that we may be able to do. So that's basically going to be the output. So thank you very much. I've kind of brought it up to about 9 o'clock now. What I'm going to do is I'm going to stop the recording now in a second. Thank you all very much for coming. I hope you found it somewhat useful. Like I said, I think there's 2 left. I'm going to stop the recording in a sec, but I am going to hang around for a little while. If any of you want to stay on and have any questions or want me to cover some of the things that I didn't discuss or you would like me to explain, I usually leave myself a bit of time afterwards to do that. So by all means, hang on if you have any questions. But other than that, thank you all for coming, and I'm going to stop the recording now. And if anyone has any questions, I can deal with them. Thanks very much.